Hello everyone and welcome to FatalSec. This video will provide a walkthrough on dynamically bypassing anti-debugging and anti-reversing defenses used in iOS applications. For the purpose of this video, we are going to use iOS Challenge 2, which is provided by OWASP Foundation as a part of their mobile security testing guide. If you want to follow along this video, then make sure to download the application link which is mentioned in the description box down below. Furthermore, I recommend reviewing their mobile security testing guidelines for iOS, especially if you are new to mobile security field. Okay, so let's start the analysis first. Here I have my jailbroken device connected to this machine, and this is the application which I have already installed, iOS Challenge 2. Let's try to launch it normally from the UI and see what happens. Whoa, the application closed immediately. Now, there could be multiple factors due to which application is getting closed or terminated. One could be because of jailbreak detection. Another reason could be because of some kind of tampering check, as we have directly installed the application on our jailbroken device without signing it with a valid provisioning profile. Okay. So to identify the real root cause of the termination, let's extract this application and open it in a disassembler for further analysis. Okay, so here is my terminal, and let me first navigate to the directory where I have this IPA file present, which is inside documents, trainings 2024, and then we have iOS challenge 2. Okay, let's list out the contents, and over here you can see we have this iOS challenge 2.ipa file, right? So as usual, for analysis I am going to use Radare this time also. But one thing to note here is that we cannot directly open this IPA file into any disassembler. Instead, we first need to extract the binary. So IPA file is basically a package which contains all the resources and framework required by the application to run. Okay, so you can consider it just like a normal zip file. So to extract it, we can simply first rename it or copy it as a zip file. So here I am going to copy it as iOS challenge2.zip. Alright, so now we have iOS challenge2.zip file present, and then we can simply extract it using unzip command. Okay, so now after extracting it, we have got this new folder which is payload. So this payload basically contains all the resources and the frameworks which I mentioned. So if we go inside it, we can see there we have iOS challenge2.app. This is also again a directory, so let's go inside it, and then we have all the resources present in the application. So these are some of the images, package info, storyboard. This is the actual binary which we are looking for, iOS challenge 2. So we can use file command just to be sure that it is an iOS binary. There you go, it says macro 64-bit executable for ARM64 architecture, right? Now to open it into Radare, we have to type R2 followed by the binary name, which is iOS challenge 2, right? Hit enter. Next, we need to tell Radare to start the analysis using 4 times A. We are not going into the in-depth analysis for now. Hit enter, and there you go. The basic analysis is done by Radare. So if we list out all the functions present in this binary, we have to type AFL command, and there we have all the functions which are identified by Radare in this binary, right? Okay, so straight away we can see some of the interesting functions present, such as is jailbroken, jailbreak test 3 tabbed. Similarly, we have again jailbreak test 1 tabbed. So it looks like there are multiple jailbreak detections present in this application. But instead of directly jumping on these functions, let's try to backtrace the flow based on what we have observed from the app behavior. Also, going backwards is generally a good idea in reverse engineering, especially when dealing with in-app protections like this one, where the application is getting closed or crashed. Okay, so coming back to the device, if you remember, when we launched the application, it got terminated immediately, right? So let's now think about various ways in which an application can be closed or terminated. The very first thing that comes to my mind is by calling exit function. So let's see if there is any exit function present in this list. And there we have it, exit function. Let's now try to find the cross references to this exit function call to figure out from where it is being called exactly. So for that we have axt command followed by the name of the function, enter, and it says that exit function is being called in view did load method at offset 8ab8. So if you are familiar with iOS programming, then you must know that view did load is a function which gets executed at the beginning as a part of initialization phase to set up and configure view controller, which is basically required to render various components on the UI. So this seems to be a good starting point for us. Let's seek to this method using s command followed by the name of this method, which we can copy and paste like this, hit enter. And now our cursor has moved from this offset to this offset, which is where view did load method is present. Next, in order to view the disassembly, we have to run pdf command. So here we have the disassembly of this function, and if you look closely, there are some interesting strings which are clearly visible, such as app is being debugged and tampering detected. Nice. To better understand the flow of this function, let's open it in a graph mode. So if we enter capital V, it will take us to the graph mode where we can clearly see the control flow graph of this method, right? So here in the first basic block, we can see that it is trying to call two functions, 8864 and 8830. Then it's making a comparison using CB and Z instruction, and if the result of the comparison is true, then it will go to this OJ block where app is being rendered string is referred. Otherwise it will go to OF block where another check is being done by making a call to 898C function, followed by another comparison using CB and Z instruction. And if the result of this comparison instruction is true, then it will again go to OJ block. Otherwise, if the result is false, then it will go to OH block over here. Then inside this OH block, another check is being done using this function call 88B4. Then if the result of this comparison instruction, which is done by CB and Z instruction, is true, then it will go to OK block where tampering detected string is referred. Otherwise it will go to this OI block from where it is simply returning back. Another thing to observe here is that from these two blocks where app is being debugged, string is referenced and tampering detected string is referenced, the flow is going to ON block where nslog function is being called, followed by exit function call. So most likely this block is being executed right before terminating the application. And right before the termination, using this nslog function, the application is trying to print the reason of the termination, which is either tampering detected or app is being debugged. So I hope the flow of this function is clear. It's pretty straightforward, nothing too complex. So what we have to do is make all these comparisons false so that it will go to the return block. Now what we can do from here is that we can simply try to hook this nslog function to figure out what is the actual reason of the termination. So for hooking, I am going to use Frida framework. And on a jailbroken device, make sure you have Frida package installed from your default package manager such as Cydia or Celio, whatever, depending on whatever jailbreak you are using. So for writing the Frida scripts, let's jump to the Visual Studio Code, which is my go-to editor. And here I have already opened this iOS challenge 2 directory where we have extracted the payload and we have this IPA file. So right over here, let's create a new script and name it as bypass.js. Okay. Now in order to intercept the nslog function, we can use interceptor dot attach API of Frida, where the first argument we need to pass is the pointer or the address of nslog function, which we can figure out by using another API called module.findExport by name. Here we can pass in null as the first argument, and in the second argument we need to pass the name of the function, which is nslog. Okay, then in the second argument it's going to be a callback function, and because we are interested in intercepting the first argument of this nslog function, we are going to use on enter attribute. So inside on enter, we have this argument called args, which is an array of arguments, and using the indices we can access the argument which we want. So over here let's just print console.log, let's say nslog intercepted, followed by another console.log where we can print out the actual argument which is present in args0, right? But we cannot directly print out the argument like this, because if you look at the argument type of nslog, let me show you how it looks like. So if we go to the Apple developer documentation for nslog, here you can see its signature, where the first argument is of type nsstring, right? So what we have to do is to typecast this argument in the form of nsstring, which is nothing but a object. Okay, so for that let's just wrap this argument inside a pointer, because it will give us the address of the string where it is present in the memory, and then this address we can utilize in objc dot object method, which will give us the object interpretation of that address, which is nothing but nsstring. All right, let's save this script at this point, and let's try to launch the application by attaching this script. But before that we need to figure out the app's bundle identifier or the package name, which we can find by using a different Frida command. So let me open the terminal here itself, and to figure out the package name or the bundle identifier we can run frida-ps -u for USB AI to list out all the packages, and here it says command not found Frida ps. That's because I have installed my Frida tools inside a virtual environment. Okay, so let me activate that. Source virtual environment bin activate, and now if I run Frida ps, it listed out all the installed packages on my device. So the one we are looking for is iOS challenge 2, and the bundle identifier for it is re.murphy.iOS challenge 2. Let's copy this and clear out the terminal, and now we can run our Frida command, frida-u for USB mode, followed by -l to list out the script, which is bypass.js, then -f to forcefully spawn a new process of our application, and then the bundle identifier, right? Before running this command, let me bring our device on top. Okay, now let's hit enter, and the application was launched, but it got terminated immediately as we expected. But in the Frida logs we can see that our nslog method got intercepted, and the argument to nslog function was also printed out on the console, which says tampering detected. Cool. We now know that the application is executing tampering detected block, which is this one, right? OK block. Now before moving forward, let's also see what happens when we attach the debugger to this application. But here we have a small problem. As soon as we are launching the application, it's getting terminated. So how can we attach it to the app's process? And I'm sure most of you also get stuck into situations like this. So let's try to be little innovative here and utilize Frida to spawn the process, but in paused state instead of running state. So to do that, let's go back to our Visual Studio terminal and in this Frida command, we can tell Frida to spawn the process in a paused state simply by adding hyphen hyphen pause attribute. And now if we hit enter, you will see that the application is started, but now it's in a paused state and it's not terminated. And in the Frida console, you can see it says use %resume to let the main thread start executing. Cool. So we have the application running, which means we have the process ID, which we can use to attach to the debugger. But there is a small catch here. As you have observed just now, the application got terminated after a few seconds, right? And that's because Springboard does not allow application to stay in pause state in foreground for more than few seconds. So we have a very small window in which we can attach the debugger to this process. Now to attach the debugger, you first need to make sure that debug server is installed on your jailbroken device, which then you can use from your device shell. So let me get access to my phone's shell via SSH. For that, let's open a new terminal and use SSH root at the IP address to which my iPhone is connected, which is 192.168.1.4. Enter. It's asking for password, which I have set during the jailbreaking process. So now we got the shell access of the iPhone as a root user. So if you remember, we have a very small window to attach the debugger. So let me also type the command in advance to run the debug server in listening mode, which is debug server followed by 0.0.0.0 to tell debug server to listen from all the interfaces, followed by the port number. I'm going to use 1234. You can use any other TCP port which is not in use, followed by -a attribute which tells debug server to attach to the specific process which we are going to mention now, which in this case is iOS challenge 2, right? Now before executing this command, let's spawn the process using Frida again in pause state. Application is in pause state now. Let's go back to the terminal, hit enter. Think it's like this. Yes. So now it's saying attaching to process this, and it's stuck over here. That's because Frida put the process in pause state, so we need to resume it from here using %resume. And now you see it says listening to port 123 for a connection from all the interfaces. Let me split the terminal now, and over here I am going to use LLDB client to attach to this process. Okay, now we are into LLDB shell. We need to tell it to select iOS SDK via platform select remote iOS command. Okay, hit enter, and it automatically detected the path where the iOS SDK is present on my machine. So if your Xcode is properly configured and iOS SDKs are downloaded, then LLDB will automatically pick it up. Otherwise, it will fetch all the libraries and symbols from the app's process memory, which will be a bit slower. So I would suggest to make sure that Xcode is properly configured and the iOS SDK is also downloaded. So now we have told LLDB to use the iOS SDK. Then to connect to this process, we need to tell it using process connect command, connect : the IP address of the iPhone where it is listening, which is 1.4, then the port which we have used here where debug server is listening, and hit enter. So as you see, it started passing symbol table for all the frameworks present in the application, and here it says waiting for debugger instruction to process. So once the debugger is attached successfully, we will get something like this where it says the process is stopped at this instruction, right? Also, just to make sure that debugger is working fine, let's also set a breakpoint. Here I am enabling the breakpoint for exit function because we have identified it, which is the one getting executed right before the process termination. So to set the breakpoint, there is p command followed by the function name. So it says that it has identified two locations where exit function is present, so it has just set the breakpoint for that. Okay, now we need to tell the debugger to continue executing the process, because as of now it's in stopped state. So for that we have C command or continue to tell the debugger to continue the execution. So if we hit enter, it says resuming and then the process is terminated, right? So going back to Visual Studio terminal, and over here we see that it shows process terminated but no log was captured. This could be because the application is getting terminated even before the execution reaches to the point where the log is being printed. So at this point we don't know exactly from where the application is getting terminated. So let's go back to the disassembly of view did load and start analyzing it one by one, starting from this function which is 8864, as this is the function which is getting called immediately from view did load method, right? So here just some basic epilogue stuff, and then we have this function call. So the first function is this one. Let's analyze it further. So to go inside this function, either you can copy this symbol and seek to that offset, or you can directly use this OB abbreviation which is assigned by Radare. So in this visualized mode itself, if I type OB, it will take us to the disassembly view of that function, right? Now this function looks pretty simple as there is only one basic block present. Here the first thing to be observed is this ptrace string. This is interesting because with ptrace you can inspect and manipulate the internal state of a process, and it can be used to detect the presence of a debugger. Okay, so here another thing to observe is that instead of calling this ptrace function directly, the application is actually using dlsim and dlopen functions to resolve the function at runtime. So again, there could be multiple reasons for doing this. Primary reason is because App Store does not allow applications having ptrace system call because it is not a part of iOS public API. And another reason is to hide the implementation of ptrace function from the attackers or reverse engineers. In this particular application, because string encryption is not present, we are able to see all these sensitive strings visible in clear text. Otherwise, you can imagine if these strings are encrypted, how difficult it would be to figure out what exactly going on in this function unless you manage to decrypt those encrypted strings first, right? As we now know that it could be used to detect the presence of debugger, let's analyze it further. So here this dlsim function will return the pointer containing address of ptrace function, which will be stored in x0 register. As per ARM64 calling conventions, you know that all the functions return value is stored in x0 register, right? Then in the next instruction, the return value, which is nothing but the pointer or the address of the ptrace function, is being stored into x8 register using this move instruction. And then after these couple of move instruction, we have a branch instruction which is basically branching to x8 register. So whatever value is present in the x8 register, that function will be called. And here we now know that this x8 register contains the address of ptrace function. And again, coming back to the ARM64-bit calling conventions, we know that all the arguments to the function are stored in the registers starting from x0, then x1, then x2, and so on, right? So just imagine here, instead of this branch x8, we have a ptrace function call, and right before that we have these move w0, w1, x2, w3 instructions present. So these are nothing but they are just storing the arguments of the ptrace function call into the respective registers, right? So if we again go to Apple developer documentation for ptrace, here you can see its signature, which is int ptrace. Then the first argument is integer request followed by process ID, then some address, and then some data, right? So the first argument is what we are interested in, which is a request. And if you scroll down, into the description section, you see that the request argument specifies what operation is being performed. So we have couple of different requests which can be passed to this ptrace function call, such as ptrace me, pt deny attach. Now this pt deny attach is something which is used for debugger detection purposes. So let's see what this request is all about. So this request is the operation used by traced process. It allows a process that is not correctly being traced to deny future traces by its parent, right? So this request basically tells the process to exit if a debugger tries to debug it, which is mentioned here. If the process is currently being traced, it will exit with the exit status of this. Okay, cool. We now know how ptrace function works, and also we have this pt deny attach request, which is going to be passed in the first argument of the ptrace function. So if we go back to the disassembly, the first argument for a function call is always going to be stored in x0 or w0 register, which is this one, move w0 hex 1f. So this hex 1f, if we convert it into integer, it's going to be 31. Okay, and let's see what this macros value is. For that, what we can do, we can look at the ptrace header file from Apple source. So we have Apple open source website here, which contains the source code for ptrace header file. And if we scroll down, we can see all the macros which are defined here, and the one we are looking for is pt deny attach, whose value is 31, right, which is nothing but x1f, which is being called here. Okay, so now we can be sure that this ptrace function is the one which is responsible for detecting the debugger, and as per the description of the ptrace function call and the pt deny attach macro which we saw just now, it says that if the process is being traced or debugged by another process, then simply exit the process, right? And this is exactly what we have observed when we attach the debugger to the process. So let's hook this ptrace function using Frida. So if we go back to our script, okay, let me copy paste this interceptor as it is, and instead of nslog, we have to intercept ptrace function. So here now it will say ptrace intercepted, and then this time we are interested in the first argument of the ptrace function, which is, if you remember, of type integer, right? So let's store the request in a request variable, and the first argument we can access using args0, and it's an integer argument, so we can convert it into integer using 2int32. Okay, so this is the request number, and this should be equal to 31, which is pt deny attach. So just to be sure and not to mess up with any other ptrace system calls in case the application is making, we can check if the request is equal to 31, then only. For now, let's just log it request. Okay, so if the request is going to be 31, then what we are going to do is bypass it. So this is just for logging purpose. Okay, it has nothing to do with the bypass. And to bypass it, actually what we have to do is to modify this request, or this request number itself, right, which is present in this argument 0. So to modify that, we can simply assign any negative number to this args0. So instead of request 31, which is pt deny attach, now it will contain -1, which is an invalid request. Okay, and let's wrap it up using ptr. This should be good enough to bypass this check. Okay, so let's save the script. Let me clear out the terminal and spawn the application again in pause state. Hit enter. Quickly go back to the terminal and run our debug server. Now let's tell the Frida to resume the process. Let me clear this as well and again go back to LLDB select remote iOS platform and then connect. So here we got the connection, and then the debugger is stopped here, right? Cool. So over here the application is still in pause state, it's not yet terminated. Now if we tell the debugger to continue the process, if we have managed to bypass this ptrace function call by injecting this hook using Frida, we should see some different behavior, or at least observe something different in the console, right? So let's see. Going back to the debugger, continue, process resuming, and then exited. So again the process got terminated, which means that the detection is still there, which is causing the application to terminate. And let's go back to the terminal over here, and in the log this time we can observe that ptrace function call is intercepted. Request we got was 31, which is pt deny attach. Awesome. And then it says bypassing it. This is exactly what we have printed over here. This means that our argument got replaced with -1, which is an invalid request. So instead of 31, ptrace function now got -1. And then this time, instead of directly getting process terminated, we have managed to capture ns log, right? And it says app is being debugged. Cool. So if we go back to Radare terminal and go back to view did load method over here, previously before bypassing ptrace function call, our application was just getting terminated without printing any logs, right? And even before that, without attaching the debugger, we were getting tampering detected. But this time we are getting app is being debugged, which is this block, OJ block, right? So if we observe the flow, this function 8864 was the ptrace function call check, which we have bypassed. And as a result, we managed to reach this block, right? Also, another way to look at it is that in the log, we are getting app is being debugged, which is this block. And now there are only two places from where this block can be reached. First one is this path, which is coming from this first basic block. And another one is this path, which is coming from the second block. So now there are two possibilities after bypassing this ptrace function call. Either this conditional instruction is causing this block to execute, or this conditional instruction which is present in OF block is causing this block to execute, right? So we have to analyze both of these functions in order to figure out from where exactly this block is being triggered. So let's start with the first one right after 8864 function call, which is 8830. So to go inside this function in visual mode, again we can simply type OC. So in this function, immediately we can observe that there is a function called to get ppid, which is get parent process id. This function simply returns the process id of the parent process, which means if the application is launched using any other program, then it will return the process id of that program. Normally, when we launch any application, it gets launched via a process called launchd, whose process id is always 1. So if you look at the next instruction, it's comparing the result of get ppid, which is stored in w0 register as per ARM calling convention, with 1. So basically, if get ppid returns 1, then it will set w0 register. Okay, so yeah, basically if the comparison of these two values are not equal, then it will set w0 register, which basically tells that the parent process id is not equal to 1, which means the application is launched or spawned using any other program. So to figure that out and bypass this, let's hook this get ppid function using Frida and intercept its return value. Okay, because that's what being compared here, right? So going back to the Visual Studio, and I'm just again copying this interceptor.attach method, and instead of nslog this time we are interested in get ppid method. So let's put this as in the log, Okay, we are interested in intercepting its return values. So instead of on enter, this time we will use on leave attribute, and instead of the arguments, it will take return value. So now let's print out the return value of this function. Return value. Okay, let me store it into a variable called ret return value, and normally it's in the form of hexadecimal number, so I'm going to convert it into int32. Okay, let me print it over here, and then let's make a if condition. So to make sure that if the return value returned by get parent process id is not equal to 1, then only bypass this check, otherwise let the app execute this function as it is. So if this return value is not equal to 1, then I'm going to put another log which is going to say bypassing it. Okay, now to modify the return value, we have to make use of this ret_val variable and then use the replace function which is provided by Frida, and over here we can simply replace it. In this case I want it to be always 1, and like I mentioned, the return value is ideally in the form of hexadecimal numbers, so let's replace it using hex 1. Okay, saving the script, and again let's spawn the application in pause state. Okay, quickly going back to the terminal and run the debug server, resume the application and run lldb again, select remote iOS platform and connect. There we go, debugger is now attached, we got signal stop. Okay, application is still running in pause state because of the debugger, and if we continue the execution it says process resumed, but then again the process got terminated, right? And if we observe the Frida log, we see that we got get ppid intercepted with the return value 1135, which is not 1 obviously. And then as per our condition, if the return value is not 1, then bypass it. So we got bypassing it, and it replaced the return value with 1. So as per our logic, this check is bypassed, but still if you see, we are getting app is being debugged message in the log. Right now this is because if we go back to the terminal in Radare inside view did load method, you see there were two places from where this app is being debugged block is reaching, right? First one is this and second one is from this block. So this time we have bypassed this function 8830, right? Now it is possible that this function is bypassed. As a result, instead of going to this block from here, the application executed this block, and then somehow this function again returned non-zero value, because of which this condition became true, and then app execution reaches here, right? So now we have to analyze this function and somehow bypass the check which is being done inside it to avoid this true condition. Okay, so for that again we need to go inside this function. For that we can type OE. All right, this function looks interesting because there is an interesting function call present which is sysctl. So again, sysctl is a function to retrieve process information in order to identify whether it is being debugged or not. This method is actually officially provided by Apple to detect the presence of debugger, which is described over here. Okay, this is a part of technical Q&A session by Apple itself. So here you see we have the whole code snippet for detecting the presence of debugger using sysctl function call, right? So let's try to understand this code snippet quickly. Firstly, it has defined 4 variables called junk, mib, info and size, and out of these 4, the one which we are interested in is this info, which is of type structure kinfo proc. Now we are not going into the details of these kinfo proc and kp proc structure. You can go to Apple developer open source code and look into these structure to figure out how these fields are present in the structure. Okay, So for now, let's just focus only on this field p flag. Then we have these mib variable array, which is initialized with process information. Basically, this will tell sysctl function to fetch the information about the process whose process id we have passed using get process id method. Then in the end, it is performing a bitwise AND operation with ptraced flag and this p underscore flag field. And if the result of this AND operation is equal to 0, then this method will tell that the process is being debugged, otherwise it will return false. So in order to bypass this detection, we have to manipulate this p flag field and assign 0 to it. By modifying this flag with 0, basically this AND operation will always return 0, because if we perform bitwise AND operation with 0, it will always return result in 0. And according to this condition, 0 is not equal to 0, which makes this function return false. So let's go back to our Frida script. And let me copy this again, and instead of get ppid, we are interested in intercepting sysctl function, right? Then this time, actually, if you see from this code snippet, the mib or the process information is being passed as the first argument of this sysctl argument, right? Similarly, this information, which is the structure where our p flag is present, this is being passed in the second argument of this sysctl function, 0 1, and then the second argument, right? So that's why by utilizing the on enter attribute, we first need to extract this information so that we can access this p flag field, right? So for that, let's use on enter function arguments. Later we will also need to use on leave, so let it be there. Now in order to fetch the information, I'm going to make a local variable called kinfo, and the argument is the second argument, right? Or the third argument basically. So as per ARM calling convention, if you remember, x0 register will contain the first argument, which is MIB. X1 register will contain this information, and then X2 register will contain the structure or the information which we want. So to get that, let's use the register X2 this time. Okay, then inside on leave, put sysctl intercepted. Okay, let's remove this. And now this p flag is part of this kp proc structure, which is present inside kinfo proc structure, right? So you can obviously go and look into these structures by yourself, but I'm not going into that much detail, otherwise it would be too much information. So for the sake of the video, what I can tell you is that to access this kp proc and this p flag field, if you just add 32 bytes into the address pointed out by this info variable, you will get p flag. Okay, so let's do that. Let me create a variable called p. Then here in on enter, we have defined kinfo variable, so I'm just accessing it over here and then adding 32 bytes to it. Okay, and then we need to read the p flag value, right? So to read that value from this p pointer, we can use read int function of Frida, and over here it's performing a AND operation with p traced flag, right? So we just need to simulate that in our Frida script. So to perform the AND operation, we can simply use AND followed by p traced. Now this p traced value we don't know yet. So to figure out what this p traced value is, let's go back to the browser, and since this ptrace flag and p flag is part of proc.h header file, we can simply look at that from Apple. And if we scroll down here, you see we have the p flag and we are looking for ptraced macro, right? So over here we have the ptraced flag, which is assigned a constant value of x800. Let's copy it and use it over here. Okay, now this statement is as good as this one. Awesome. So what we can do now is we can simply check if this p flag value is equal to hex 800. This means that we need to bypass this check, bypassing it. Okay, so in order to bypass, we just need to replace this p flag with 0, which is the default value assigned over here. And if the p flag turned out to be 0, this whole AND operation becomes 0 and this condition will become false, right? So to override that, we can use this p pointer and then write int function of Frida to write 0. Okay, that's it. Hopefully this is good enough. Let's save the script and run it again in pause state. Quickly going back to the terminal and run the debug server, resuming the process from Frida shell and attaching the LLDB again. Okay, cool. Continue. Process is resumed and then we got process exited again. So still there are some detections left, but if we look into the console now, we got sysctl intercepted and then bypassing it. Nice, which means this condition became true and we have replaced the p flag value with 0. And as a result, if you observe closely, this time instead of getting app is being debugged, we are now getting tampering detected. What does it mean? It means that we have bypassed the debug detection checks which are present in this application, and now we are ended up with tampering detection. So if we go back to Radare terminal, in view did load method, now instead of going to this app is being debugged block, we are getting tampering detected, right, which is this block. Okay, so again, by using the same methodology, let's figure out from what all places this block can be reached. So this one is quite straightforward. There is only one path from where this block is reaching, and that is from this OH block, right? And in this OH block, there is only one function which is being called right before this comparison instruction. So let's look into this function, because this function is most likely the function which is detecting the tampering. So to go inside this, let's type OG and there we have this function. Looks interesting. Because the application lacks string encryption, we can clearly see the strings such as substrate, size script, SSL kill switch, Frida, and all these frameworks are usually present on a jailbroken device. Then in the next block, it's making a call to dyld get image name function, which is used to verify whether these frameworks are present on the device or not. If they are present, then this function will return the full path of the framework, otherwise it will simply return null. Then after this function call, if you observe, we have this strstr function call being made, followed by a comparison instruction, right? And if you look at the definition of this strstr function, it will tell you that it can be used for string comparison or substring matching, right? So let me quickly explain you this particular block. So over here, basically it has initialized this x21 register with substrate string, then x22 register with sysctl, x23 register with SSL kill switch, x24 with SSL kill switch 2, x25 with Frida string. Okay, once all these registers are initialized, then over here, if you look, this whole code is part of a loop. Okay, this green path, if you follow, it's coming from here, so it's going one by one over all these strings. Okay, so inside this OF block, the application is making a call to dyld get image name, where it has passed, then the result of this get image name function is stored into x26 register, which is then passed on to strstr function with the one present in x21 register, which is substrate string, right? So in short, if you don't understand this assembly, it's iterating over all these string, making a call to get image name, and then whatever the value or the path returned by this get image name function, that is being passed into strstr function. So this strstr function will take two arguments. First one is this one, the value returned by this function, and the second argument is going to be the hard-coded string with which the comparison is being made, which is one of these string. Okay, so that's how this function is basically detecting whether any of these frameworks are present on the device or not. Now to bypass this, what we can do is either hook this get image name function and modify its return value, or we can hook this strstr function and modify its return value to 0, which tells that the string is not present. And I would suggest to hook the strstr function, because sometimes dyld get image name function is used for legitimate purpose as well by the operating system as well as by the application. So if you hook this function and manipulates its return value, this could make the application unstable. Okay, so let's write a hook for this. Going back to the Visual Studio editor, and again copying this interceptor.attach. This time instead of sysctl, we are interested in strstr function, right? And again on enter and on leave attributes are required, because first we are going to intercept the arguments of this function and then we will modify its return value, which we are going to do inside on leave. Okay, so inside on enter, actually let's use the same approach. Let me first create an array of these libraries. So the first one is substrate, then sysctl, then SSL kill switch, then SSL kill switch 2, then Frida. Okay, so now all the libraries or the frameworks which are being detected by that function, we have all those over here in this temper libs variable, right? Now inside on enter, let's create a variable called I, which will contain the length of this string, and then I'm going to create a local variable called using temper lib and assigning it to false. You will see later on why I have created this variable. I'm going to use it as a flag, and then just like the application what we saw, it's iterating over all these strings one by one inside a loop, right? So we are going to use the same approach. For that I'm going to use a while loop, while I minus minus. So I will contain the total count of the libraries which we have defined over here. In this case it's 1 2 3 4 and 5. So our loop will start with 5, and then inside this while loop I'm going to extract the argument, okay, and then read it in the form of a string using readc string. Okay, then if library name is equal to one of these libraries, right, then let me put a log over here which says strstr invoked using library name, and then we will bypass it. Okay, so this time I am going to make use of this flag and set it to true. Okay, then inside this on leave method, all we have to do is check for this flag. If it is true, then we need to just replace the return value using dot replace function with 0. Okay, I hope it's clear. So let me quickly walk you through this code. Firstly, I have initialized the I variable with the total count of the libraries. Okay, then I have declared a flag variable and assigned it to false. Now this variable is local to this interceptor. Okay, Then using this while loop, I am iterating over this temper library array one by one and fetching the first argument of the str string, not the first, the second argument using the first index, right? Because the index starts from 0. So if the library name which is being passed in the strstr function is equal to one of these libraries, then basically it will tell that the suspicious framework is present on the device. We need to bypass it, and for that I have used this flag and set it to true. Then in the on leave method, if this flag is true, I am simply replacing the result of strstr function with 0. Okay, if the strings don't match, strstr function always returns 0. So that's how this bypass works. So let's check it out quickly. Clearing the console, spawning the application in pause state, quickly going back to the terminal, running debug server, resuming the process, and again launching LLDB, selecting remote iOS platform and connecting it. Okay, process is stopped. Application is still there in pause state because of the debugger. And then over here we have our Frida console, right? Let's continue the execution from the debugger. Process resuming, and this time interestingly the process is not terminated, it's still running, which you can see over here. The application is launched now, and in the log you see our strstr function is invoked with all these strings one by one, and we are bypassing it. Awesome. So far we have managed to bypass the debugger detections which are present in this application, as well as the temper detection, which are nothing but these framework detection. I hope you enjoyed this video and feel free to try it out by yourself. If you are still here, then don't go without subscribing to the channel, as this is what keeps us motivated in making such videos. And feel free to comment in the comment box down below if you have any queries or want me to improve anything in the next video. You are also welcome to join our FatalSec community on Telegram and also follow us on X as well. Thank you so much.